This presentation talks about maintenance. Maintenance is an essential thing in terms of achieving productivity in the workplace. If you look at this mocked up picture of a company car, if you get a company car when you graduate and it's in this condition, it's pretty obvious that you're not doing any maintenance. So, what about the equipment? It's not so obvious a lot of the time. In fact, a lot of the Japanese philosophies say the first thing that you do is clean the equipment so you can see the faults. Why is it surprising? Company car is only 20k, whereas a web press or a big piece of capital part can be millions. Throughout this presentation, the examples will tend to be drawn from the printing industry. And the reason for that is we were commissioned a couple of years ago to do a survey of maintenance in small businesses and large businesses involved in the printing industry. So, why should you want to maintain? Well, you want to maintain because you want things to be available and you want things to be reliable. If your car was badly maintained, you'd have a trauma every time you wanted to get up, every time you wanted to start the car on a cold winter's morning. I've got to go to work, I've got to get up that bit earlier. Because my car isn't maintained properly, I can't guarantee that when I step in it, turn the key, it will start. Does sound a bit like some of my cars, so that means I get up quite early in the mornings. Why do you need reliability and availability? Because you've got to satisfy the needs of your customer. Your customers want shorter run lengths. They want to have shorter lead times. They want to turn around and order a piece of material from you and you deliver it the next day, preferably. Normally they want you to deliver it yesterday, but very short lead times. You need to deliver a consistent quality. If the equipment's not very well maintained, it'll tend to drift, it will tend to produce its own inaccuracies. So you have inconsistency. Inconsistency equals poor quality. And you want to be able to offer to your customers just-in-time delivery. You want also to get a better return on your capital investment. You want to be able to run at higher production speeds, so that you can produce more production, which means if the thing breaks down, you lose more production per minute. You also, if your machines can be driven harder, you need less spare capacity, which means you need less manpower and you need less capital investment to produce the same amount of goods. Without a maintenance strategy, companies go into the spiral of breakdown despair. They lose production because of breakdowns and because they can't run their equipment as fast as they would like to have designed to run it. So because of that, they're not meeting customer deadlines. So they have to run their equipment harder to recover lost time. By running it harder doesn't mean they're running it faster, they've got to run it for longer hours. Because it's still not being maintained, you move to position 3 on the spiral of despair, where breakdowns increase because the thing isn't being maintained, and more time is lost. Because more time is lost, we've lost more productivity, we've lost more production, there is more pressure to get the jobs out, and we spiral down in 4 to a point where there is less time available for maintenance. Ultimately, the plant will spiral down to a point at which it doesn't work at all and the whole production ceases. If you're in the position where you have a car and your car you need every day, because you need it every day, you haven't got time to maintain it, eventually you reach the point where your car is unavailable because it breaks down catastrophically. How important is maintenance? A survey a few years ago estimated that the total cost of maintenance in the EU approached 5% of the total manufacturing turnover. That's equivalent to the total annual industrial output of Holland. It's a big and important aspect of engineering. There are around 2 million people in 350,000 companies engaged in maintenance activities. But as we'll see from the study that we'll show later, they do not necessarily class themselves as being in maintenance. It is just one of the tasks that they do. We spend a lot of time teaching you how to design properly, but 70% of diesel engine failures are due to contamination. Contamination, 50% are due to wear, and wear-related issues, i.e. not maintaining your equipment properly. 40% of rolling element bearings fail because they use the wrong lubricant. Only 10% fail because they got the design wrong. So we're looking at an issue which has a big impact on the things that you will be designing. If you look at gearboxes, 75% of gear failures are due to service problems. And if you look at the first 5 of these, incorrect lubrication, foreign materials, these are maintenance issues and not monitoring the performance of the gearbox. So in fact 51% of the failures are related to wear and 49% are related to overloading. So the big problem is not that we overload the gearbox, but we don't maintain it properly. Of course, one of the interesting things is, what is a failure? A failure is different things to different people. One man's failure is another man's inconvenience. If a gearbox operating in a continuous process plant production line fails or shows signs of failing, if the safety office are involved, they would call for an immediate shutdown because the plant isn't working perfectly. If the production manager is involved, he's being pressurised by the people in sales saying, you've got to get this production out, and by the senior management, he'll say, it's still running, let's leave it run, and we can inspect it the next time we have a shutdown. The sensible way of doing it, if you have somebody who's looking at the maintenance issues, is you stop the gearbox, you stop the production line, you inspect to see what's happening, and then you monitor to see if it gets worse. And then on the basis of the inspection and the monitoring, decide when it's going to be dealt with. The history of maintenance is very parallels with what goes on in the National Health Service. In the 1930s, we used to have breakdown maintenance. If you had a heart attack, then they'd try and recover it after the event. If you had something go wrong with you, you'd end up with having surgery. In the 1950s, people to start thinking about preventative maintenance. In terms of the heart, preventative maintenance could be having bypass surgery so that you have a good blood flow to the heart muscles so that you don't have the heart attack. This is the same as periodic component replacement. In the 1970s, you started to look at predictive maintenance. We're now starting to look at disease detection. Is something going wrong ahead of time? Monitoring blood pressure on a regular basis, for example. This is condition monitoring, identifying that something is failing and fixing it before it fails catastrophically. Finally, in the 1980s, we get proactive. You start looking at cholesterol and blood pressure monitoring, the root cause being diet and diet control, so people start looking at what they eat. Tremendous amount of studies published all the time about what things are good for you and what things are not good for you. This is the same as performance monitoring, contamination control, total productivity maintenance. What are the maintenance strategies we have available to us? The first and most basic is breakdown maintenance. Breakdown maintenance is we let the plant run, when it breaks down we fix it. The second strategy is restorative. This used to be very popular. Once a year or once every 6 months, the equipment is taken out of service and is completely restored to as new conditions. The other maintenance strategy is preventative maintenance. You change something ahead of time before you know it's going to fail. A lot of effort's been put into that area to predicting failures and therefore being able to estimate when you need to change things. Most common example you'll find of preventative maintenance is changing the oil and the oil filter in your car. We'll then move on to condition monitoring. Condition monitoring looks at measuring the performance of the item and looking how that is changing. Formula One do it all the time. They are effectively doing condition monitoring on their car all the time it goes around the circuit. Not every company's got the same budget as a Formula One racing team, but it's still an important way of ensuring you get high availability. And the final aspect of the final maintenance strategy is proactive. Now I'm going to go through these in a bit more detail. But first, how do you decide what strategy you should adopt? Well, it depends on how long you expect the components to last and how long you expect the plant to last. It depends on what effect the failure will have on the process. Will it cause the process to stop completely? It also depends on whether it's detectable. Are you aware before it's too late that the process has failed? A good example is car brakes. You need to know the car brakes have failed before you put your foot on the brake, not when you put your foot on the brake. So what are failure consequences? What are hidden failures? Hidden failures are failures that are not apparent to the operator. Think again of the car brake. If the car brake fails, it's not immediately apparent. You could belt down the motorway at 100 kilometres an hour, 70 miles an hour, and be totally unaware that your brakes are not going to work. So that's a hidden failure. The first time you became aware of the failure, when you come to the end of the motorway and you can't stop. What about safety and environmental consequences? So hidden failures, things that that the operator can't see. What about safety and environmental? Well, if something fails, does it make the system unsafe? Or in today's climate, does it cause you to have an environmental problem, discharging some smelly liquid into a site of special scientific interest? And finally, the economist one, operationally. Does it make your equipment run not as well as it should do? So, what are hidden failures? Not apparent to the operators. Protective devices which do not fail safe. For example, fire alarms. Are you worried that you put a fire alarm in? You want to know a smoke detector. You want to know that it detects the smoke. If it fails, you wouldn't know it has failed until you've had a fire. So it hasn't actually caused any harm. But because it's not working, you're exposed to the risk that if there is a fire, you won't be made aware of it. So in itself it's harmless. It doesn't matter to you whether the fire alarm works or not, because it doesn't affect your day-to-day living. But it leaves you exposed to a catastrophic fire where you don't detect it. In which case, you've got to eliminate the risk. You eliminate the risk with a fire alarm by pressing the detector to make sure, the button on it to make sure that the battery is okay. You blow a candle smoke into it to make sure it sounds off, or you burn the toast, which has much the same effect. What if the failure is hidden and doesn't have a consequence? Then you've got to ask, what on earth is that piece of equipment there for anyway? It happens It might seem a statement of the obvious, but it happens quite often in industrial plants. They rebuild the plant, they redesign the system, and they leave old bits in place which are still working, but they don't actually affect anything. So you actually have to look at it and think, well, if it's not has any effect on the process and it doesn't affect safety or anything like that, why in fact have we still got this piece of equipment? Safety environment's the most important. If we had the failure, does it kill someone? Will it cause a serious injury? Will it let something that damages the environment? If the answer to either of those questions is yes, then you cannot risk having that type of failure. You've got to look at the design, redesign the process, and eliminate it or minimize the risk. A lot of the time, though, we're dealing with maintenance and we're looking at the operational consequences. What maintenance strategy we're going to adopt depends on how it impacts on the productivity and the ability of the company to make money. The economic decision is made by, does it reduce the availability so you lose productivity? Does it impact on the quality of the goods that you can produce? A good example of that, if you work in a clean room, you need to maintain the filters, because if you don't maintain the filters, the room doesn't maintain its clean room standard, and you end up getting dirt in the components that you're manufacturing. Does it create a loss of service? By a loss of service, it means, is it something that's not available, you're not able to deliver? There are some non-operational consequences. If you look at, for example, a pump failure. If you have a pump failure, a standby takes over straight away. In oil refineries, there's quite often a backup pump system. Then you have to ask the question, if the pump fails, how long does it take to repair? And while this pump is being repaired, are you exposed to a risk that the second pump will fail? And how long is it acceptable to be exposed to that risk? And what would you do if you do have the second pump fail? So now we're going to look at the different strategies. What's breakdown maintenance? Breakdown maintenance is when something fails, we fix it. The most basic example of that is the light bulb. If you're in the house, you wouldn't change your light bulb until it goes out, because there's no point in changing it before then. You want to get it to last as long as possible. Doesn't need any planning. The only planning you have to do is make sure you've got a bulb, and make sure that somebody is there who's capable of changing it. If you have a breakdown maintenance, there must be no health and safety implications. How could a bulb have health and safety implications? Well, if it was in a dark coal cellar or on a dark set of steps and the bulb went out, you might have no lights that would enable you to see up and down the steps, so people are then put at risk. How long does it take to repair? Do you have to have it fixed straight away? In which case you might just have to wait, get a bulb from your cupboard and put it in the holder. Or can you actually afford to wait until you can go down the shops and buy another one? So, breakdown maintenance, replacing things when they break. What's the cost? There's a cost to everything. You have a loss of availability. You have all these lights in the house because you want them to be lit like that. You either lose the ability when the bulbs go out, or you maintain a surplus capacity. That is, more bulbs and more bulbs there than you actually need. You have a high spares inventory or long downtime. Well, do you keep a bulb in the cupboard, or do you have to wait till you go down the shops? You need to maintain a breakdown crew. Well, most people, I would guess here, could change a light bulb. But If it was my elderly mother, she would have to wait till one of her younger relatives came in to change the light bulb. They would be the maintenance crew, the breakdown crew, or an external contractor. So a company has a choice. Do we have a maintenance crew on site all the time who are sat around doing nothing most of the time because they are waiting for the breakdown to occur, or do we wait until we call in enough people to fix a serious breakdown? An alternative to breakdown maintenance is preventative maintenance. In preventative maintenance, you change components before they fail. Good example, changing the oil and the filter in your car. You can plan the shutdown to do it. I'm going to change the oil in my car, I will change it this weekend. So you can integrate it easily into the work schedules. You can avoid breakdowns provided you have the interval between the component replacement correctly calculated. That is, that you know that the component is likely to last longer than your interval that you've allowed for changing the oil. It assumes that there's age-related failure. It assumes that as a component gets older, it's more likely to fail. You start off with initial performance. It has to exceed the desired performance, or else you've got a failure before you start, and that's a design issue. As time goes on, the performance of the system deteriorates until eventually you reach a failure. The idea is that with preventative maintenance, we change the components before you reach this failure point. It's very popular with academics because there's a lot of effort put into forecasting when this failure point will occur, and it becomes quite popular with maintenance engineers because there's a whole raft of strategies they can talk about in terms of failure and predicting the point of failure. So what's the cost of preventative maintenance? You never achieve the full life of the components. You are, by definition, are changing them before they fail. If you frequently replace components, you're throwing money away. It also may not improve the reliability. If we look at the probability of failure, the traditional time-related, age-related failure suggests that you have a period of run-in. It's called infant mortality. There's a lot of synergies drawn with the way in which the human body behaves. So when things are young, they tend to fail. Then you have a period of almost constant failure, where you have the odd failure due to unforeseen circumstances. And then at the end, in stage 3, you have increasing failure. So provided you can predict when this transition from stage 2 to stage 3 occurs, you can predict when you should do your preventative maintenance. This slide sums up what I just said in that last bit. The initial failures, constant risk, rises generally slightly. It's the normal operating region. You have the initial failures, quite often described as running in. When you used to have a car, you used to have a period of running in. In fact, in the 1940s, 1930s, they would have a running in oil, and I think that went on right up into the 1960s, because this is the time when most failures are likely to occur. And then you have the wear out region, which is when you need to replace. In civil aircraft, 4% of components follow the bathtub curve. 2% follow the bathtub curve without the burn-in section. And 5% follow section 2 only, with a steady increase of failure. So the significant thing of that, only 11% of components in a civil aircraft show age-related failure. So replacing it at a predetermined interval is probably not good news if you're flying. So, if it's not an age-related failure, how do non-age-related failures look? Well, these show a basic constant failure with time. And there are three ways in which it gets to that constant failure. It could start off at constant failure to start with, and it just runs at a constant rate all the way through. It could rise up to a constant failure. After a period of running in, it reaches a constant failure rate. Or it could fall to that, infant mortality again. So how do these non-age related failures look for civil aircraft? The probability of rising to a constant level, 7%. Constant failure rate, 14%. Probability of a fall to a constant level, 68%. So basically, once you have the component in there, the probability of failure is much less once it's been run in. If you top that up, 89% of components on civil aircraft have non-related, age-related failures. So why is this? The first thing is there's multiple modes of failure. If you have a component, it fails when one component inside it fails. So you're looking at a multitude of different failure modes within a component of the individual, within a device of the individual components. The more complex, the more modes of failure there are. The classic example of where companies have taken advantage of this is in computers. Computers traditionally follow curve through. They start off at a high rate of failure. They have infant mortality and burn-in, and then they fall to a constant low risk. The people who identified this quite smartly were Dell when they wanted to break into the computer market. When Dell first started selling computers, they used to sell them with 2 years, 24-hour replacement warranty. How could they afford to do that when other companies were charging a large amount if you wanted to get that sort of service? Well, they'd worked out that if they ran the computer on the desk for 36 hours before they shipped it out, then it would run for 2 years without failing. Or there was a good probability it would run for 2 years without failing. If something happened in transit, it would fail immediately. So they'd have to ship it back and change it. But the chances are once it was up and running, it would run for 2 years. And because of that, they made large inroads into the market. We bought them because it meant we had computer availability all the time. So, if we can't rely on age, what can we rely on? The alternative is condition monitoring. Condition monitoring is a method of extracting information from machines that can indicate their condition. If you look to the human, you're looking at blood pressure, you're looking at body temperature as means of condition monitoring. With condition monitoring, we are looking for the onset of failure. We know what the normal operating conditions are. We can be monitoring temperature, we can be monitoring vibration, oil condition, or power consumption, and we're looking for a change in those parameters and a change that we know is an indication that failure is on its way. The critical thing with condition monitoring is identifying the key things we need to measure for any particular piece of equipment, for identifying how long it between realizing that a failure is going to occur and the failure actually occurring, because that would set the interval at which you have to do this condition monitoring, and it also sets the interval as to how fast you have to respond. There's no point in knowing that something is going to fail and then responding so slowly that you get breakdown. You may as well not bother with condition monitoring at all and just have breakdown maintenance. So, principal requirements of condition monitoring. We need to know how to detect the onset of change from a benign mode, when things are happening and just drifting about all the time, into an active failure mode. We need to be able to work out from that how severe it's going to be and where it's located and how fast it's going to occur. And from that we can decide what we're going to do. So, What are the basic methods of condition monitoring? Well, the most basic of all is performance monitoring. You monitor how much energy is going into a piece of equipment to see whether it's absorbing more, because as things wear down they might start to rub a bit more, so they absorb more power. You look at the quality of the products that are coming out, you start looking at your SPC data, or you start looking at that actual power output. So that's all performance monitoring. Things perhaps you should be doing, but looking for trends to indicate when you should be doing maintenance. The most popular in the condition monitoring armoury is vibration monitoring, putting sensors on and looking at how the vibration is changing with time for looking at indications of failure. You actually are all equipped with vibration monitors. You listen to the sounds of things, and you feel vibration in things as you're driving, as you're going along. When you're used to operating something or driving something, you become acutely aware for when there's a change in the frequency, in the note of the vibration, because that might indicate that there's a failure about to occur. For my sins, I've driven over for many years a Lotus. Lots of trouble, usually serious. You get used to listening for the wheel bearing failing, because it has a tendency to fail, and the universal joints. You know when the vibration is occurring, and you know you've got to do some routine maintenance, or else you're going to have an expensive garage repair. Visual can look at how things are looking, but more important visually is temperature. You're looking at using infrared to look at how temperature is building up in components. You can also use sensual monitoring. It's nothing too suggestive. It's that if you put your fingers on something, you can tell if they're hot. And finally, lubricant monitoring. This university used to specialise in lubricant monitoring, and it's from one of my colleagues that a number of these slides were obtained. We're looking at the condition of the lubricant, the chemical composition, and wear debris. If you think about your car, you really should be looking at the condition of the oil rather than just changing it at a set interval. So, performance monitoring. What sort of things can we monitor? We can look at, for pumps, we can look at the pressure they deliver and the power they consume. If we're looking at presses and rolling mills, it's again power consumption. And the other most important thing is you have the bill from your gas and electricity suppliers. Are you suddenly get a rapid increase? That can indicate that something is going wrong. Vibration monitoring. You get a number of key issues and different signals dependent on the type of the frequency of the signal that you have. If you're looking at a shaft, if you have a misalignment, it occurs with a peak where the frequency corresponds to the shaft speed. If you have something that's loose, then it can be 1, 2 or 3 times the shaft speed. If you have imbalance, it has a peak at the shaft speed. Gear damage, it happens at the meshing frequency. Yeah, as every tooth comes together, they hit each other. If there's a bit of damage, it occurs on a cyclic basis. If you have oil whirl, which occurs in bearings, you can get it at a fraction of the shaft speed. And with rolling element failures, that like you get in ball bearings or roller bearings, then you get a much higher frequency, because the rollers are going round, and if one of them is damaged, then it will give a spike of high frequency noise, because they're rotating much faster than the shaft. Now, the analysis of vibration is a specialist topic, which again we used to specialise here in this university. You will still see evidence of that in some of the experiments that you've done over the years. Thermal imaging. If you use a thermal imaging camera, you can look to see whether there are hot spots. You're looking for hot bearings, you're looking for systems that are about to fail. We were involved in a project which was about getting a measure of hot bearings as they pass the set point, so you could monitor if the bearings were going to fail in a train in a goods train. Why do you want to do that? Well, if the bearing fails in the middle of the Channel Tunnel, it's a long way to drag the train out. And so they were looking at a way of monitoring the temperature of the bearing housings. The reason we were involved was because they wanted to move the bearing houses from outboard, where you could easily put a temperature detector on them, to inboard, because it made the construction of the rolling stock easier. But that meant you couldn't see the bearing housing. So we were looking at a way of optically getting in to see the bearing houses. So another critical one, you'll see them flying with helicopters and the thermal imaging, looking down power cables, because you can start to see where short circuits are occurring and where the insulators are starting to break down because they get hotter. We look at any rolling component in a press. So thermal imaging, reasonably low cost nowadays. We're about to replace one of our thermal imaging cameras, and we're talking of under £1,000 for a basic model. The lubricant carries out many roles. It acts as a fluid film holding apart the surfaces under load. It acts as a coolant. It carries away contaminants. If you want to worry about why an oil turns black, it's because it's carrying away the soot contaminants, generally inside the cylinder head in your engine. It acts as a hydraulic medium. That is, it develops hydraulic forces to hold the fluid apart. It also protects against rust and corrosion. So, what ways have we got to examine this? The first and most basic is simple sensory tests. By sensory, look at it. If you look at these three examples, on the left is brand new lubricating oil. It's perfectly clear. You can see through it, you can see the line paper behind it. The next sample is one that's been in service. You can see it's picked up a few contaminants and you can't see the lines on the white paper through it. And finally, the sample of a well-used piece of oil, which is black, fully contaminated and looks like it needs to be changed. The benefits of oil analysis? The US Air Force uses oil analysis to look at serious problems in aircraft components. They reckon it saved them $15 million. The US Navy, on a similar oil analysis program for aircraft systems, reckon that it saved over 1.5 times the cost of actually doing the oil monitoring. When you're looking at in oil, you're looking at the wear and the wear particles. What happens is that the wear debris is entrained into the oil particles and taken away from its site of production. By looking at the shape and the size of these wear debris particles, we can identify where the wear came from, and from the chemical composition, exactly where in the engine it occurred, and whether it's a benign problem or whether it's something we needed to act on immediately. What we're looking at is the changing size and distribution with time, which is shown in the diagram in the top right corner. We're looking at the shape. We're looking at the analysis of the material. The other thing which goes through in the bearings and in the lubricating system is re-entrained debris. That's debris that has got past the filters, and foreign debris. Again, bits that have just got into the oil which shouldn't be there. An idealized representation of the wear is very similar to the bathtub curve. You have a reactive zone where you're getting the initial wearing off the high peaks in the bearings. You get a proactive zone where you're having benign wear, where the material is suffering age-related wear, and then you have a reactive zone where wear is increasing. Bearing wear and wear of rotating components such as this are one of the few things that follow an age-related curve. There are several ways that we can look at getting the particle features and the wear characteristics. The firstly is that we can take a regular oil sample, and offline we can measure the oil, we can measure the size and the shape of the debris. This gives us more information but isn't instantaneous. Various ways we can take a sample from the filter. We can put a magnetic plug into the bottom of the bearing case. We can also look at online measurements, looking at measuring, say, the transparency of the oil as it's rotating, or looking to monitor the metallic parts as they're recirculated. Spectrographic oil analysis is about measuring the chemical composition. You can look to see whether the oil is carrying trace elements. It could be carrying copper from a bearing surface. As the bearing deteriorates, the amount of copper increases. Also, because in most systems the oil will lubricate several surfaces. In a domestic situation, think of the modern car. A lot of the time the oil that does the gearbox also does the engine, so you need to identify where the oil which component is failing. By doing spectrographic analysis, that is looking at the chemical composition, you can use it to identify which bearing is failing, because each of the bearings has a different chemical composition. Swansea Laboratory Services, which is a spin-out company from Swansea University, has for a long time looked at the London bus fleets to identify and monitor the change in oil compositions, to identify when buses should be taken out of service, and also used extensively on North Sea oil rigs to identify which components are going to fail. There are several ways of getting at the metallic parts in the oil. One of the most common ones for iron-based debris is to use a magnetic detector plug. If you buy an old Jaguar, you find these come complete with a magnetic detector plug. These hold on to the iron particles or the steel particles, and then you can remove them and look for the debris. Other ways are to actually filter and take the debris out. If you look at representative debris, this is from an Rolls-Royce 199 engine. Once you extract the debris, you can look at the different types. You can look at benign rubbing wear. This is where components have come off and have come off as almost flat platelets because they've rubbed off. You can have cutting wear. If you can remember back to level 1 when I talked about metal cutting, this is metal cutting on a micro scale, so you have effectively a cut chip. You can have seal debris. The seal debris is non-metallic, so it wouldn't come out on a magnetic plug. You can look at fatigue wear. Fatigue is where you have breakup along the grain boundary, so the metal comes out in lumps. And you can look at general contaminants. Contaminants and nondescript particles have just happened to have wandered in there. So by looking at these different types of wear particles, we can identify where the wear is occurring. This table gives a typical set of examples of the different types of particles and how they would look. We've tried over the years to make it an intelligent system which actually automatically looks and identifies the different shapes of the particles. But at the moment it's generally proved that it's better, and human operators are actually more reliable than their image processing equivalents. But in time that may change. The other thing which you can see in the particles is when their particles heat up, for example in a wear particle, it can actually change colour. As you heat steel up, so it changes colour. So you might be able to see high temperature wear in some of the particles. So, finished condition monitoring. What about proactive maintenance? Proactive maintenance is similar to failure mode and effect analysis. It's about identifying and eliminating the causes of failure. Instead of monitoring a bearing for failure, if we identified that the failure is caused by the ingress of material, say sand if you're using it in an environment like Swansea Bay, then you could look at how you could stop the particles getting into the bearing and ultimately stop it failing. So, what's the cost of maintenance? We're looking at the cost of the item and its consequential damage if it fails. What about an unscheduled failure? Well, then you have loss of production. To prevent unscheduled failures or to minimise their effect, you have to have a maintenance team on standby, another cost. Or you have to be able to call in a contractor at short notice. If you replace things early, like you do with periodic replacement, then you're not getting the full life out of the component. You're throwing away components that could still run for another length of time. If you look at condition monitoring, the cost is the cost of equipment, the cost of training. So people have to and the cost of establishing these relationships between how much the wear is taking place, or the condition monitoring, or the vibration is taking place, and how long it is between the change from benign operation to failure. Over time, with most companies, we'd expect to see them having a changing maintenance profile. If they're serious about productivity maintenance and making their system more cost effective. Initially, most companies would rely on a breakdown maintenance approach. You run till it breaks and then you fix it. You then might move to a second stage, which is a restorative maintenance. You have a certain amount of breakdown, but periodically you restore it to its original health. Stage 3 would be you start looking at replacement maintenance as well. And stage 4 is that you would start to have a combination of breakdown, restoration and replacement and condition monitoring. So how do you end up with this deciding which of these you should use? You have to have a maintenance strategy, and the maintenance strategy depends on each element, deciding on the possible life, the failure consequences, as we've discussed previously, and the safety and the hidden failures, safety and environmental, and the economic consequences. So, for example, you might have light bulbs, which in an office you would have somebody come round periodically. You'd have enough light bulbs that if one failed, you just have a slight loss of light, nothing too serious. You have somebody come along and periodically change the bulbs as they fail. If, however, you've got a big warehouse and to change the bulbs requires you to scaffold a crane, then you might decide that on one weekend you will change all the bulbs once so many have failed, because it's cheaper to put the scaffolding up and rebulb the whole of the bay area. You might decide that if you have a light which is in a dark stairwell, you have to have an emergency lighting system should the one fail, because it will be a health and safety hazard. So for each element you're looking at it to decide, do you use breakdown, do you use replacement, or do you use condition monitoring to control, to maintain the equipment. A few years ago we did a survey for the UK government looking at the benefits of a maintenance programme. We surveyed about 100 companies. We went round and did individual interviews with their maintenance staff and produced a report, which I think is still the reference in the printing industry. We asked people what did they see as the benefit of actually having a maintenance program. They said they had less unplanned stops. They knew when things were going to fail and they were able to adjust their production schedule and plan accordingly. They were more aware of their equipment performance and capabilities. Quite interestingly, with a lot of the equipment, they have to use the original equipment manufacturer's consumables. But as they got and did their own maintenance program, they were able to identify the source of these that the original equipment manufacturer was getting them from, and buy a replacement of as good, if not better, quality. They also get to know which spares to have in stock. In one example we were given, they had purchased a machine, and the company, it was for folding and cutting paper, and the company had provided a whole set of spares that they thought they were going to need. This is the supplier company. And over a 2 or 3 year period, this box of spares gathered dust in the corner of the manufacturer of the customer of the printer's office. And yet they'd had to change components. So over a 2 or 3 year period, they had worked out which components failed, which had an impact on their productivity, and they then stocked those particularly so that they didn't have any breakdown issues. So what does that tell you? Well, actually the people operating the equipment end up knowing more about how reliable the equipment is than the original manufacturer. Think about when you've done your design in engineering. You've done your design. If you're out in industry, you do your design, and it goes out into industry, into the customer, and you actually don't know whether how well it's performing. If you get hold of some of the service manuals for cars, you actually find that as they have identified problems from the cars being in service, when the car comes in for its routine service, you will have components changed as part of the routine maintenance of a new car. The other benefit of a maintenance program is you can adapt it to suit the diverse operational needs. Somebody who is running his equipment very hard will have one sort of maintenance program, whereas somebody else who is running the equipment perhaps more slowly because of the type of product they're producing will have a different maintenance requirements. Companies with a maintenance system and those without. We found that those with a maintenance system ran faster, but did they run faster because they had maintenance, or were they running faster and so they found they had to have a maintenance schedule? Don't know. Which came first? What about long breakdowns? We specified this as being longer than a shift. For the companies with a maintenance system, they have more times when they don't have a long breakdown. Some of the companies reckon they never had a long breakdown. They had at most one long breakdown per year, whereas all the regular short-term breakdowns for the companies with a maintenance system are smaller, showing an obvious benefit. The interesting thing is short stoppages. You could argue, well, they didn't have any long breakdowns because they had a lot of short stoppages. If you look at the ones with a maintenance system, they had a short stoppage of 10 minutes to 3 hours every day. Well, perhaps they had that, but because they have a maintenance system, they were aware that they were having these short stoppages. You have to question whether the companies without a maintenance system did actually know how much stoppage they were having. A lot of the modern equipment is fitted with machine monitoring sensors. Those with a maintenance system tended to monitor them continuously, or have them monitored by the operator, or use an external surface. Those without a machine maintenance system tended to only look at the machine sensors when something goes wrong. And you have to suspect they looked at the sensors when something went wrong to see who they could apportion the blame to, and as to whether they could actually claim the money back from one of their suppliers. Another interesting thing is the occurrence of following the manufacturer's maintenance procedures. The fact that some of those with the maintenance facility or system didn't follow the manufacturer's maintenance procedures at all is perhaps because they decided that they actually understood the machine better and so had worked out their own maintenance procedures. It's also that they don't do them precisely. It's again, they get to know their machines, they get to understand how often they need to do things. So in some cases, particularly those with a maintenance system, would do more. I can give you another example from my Lots of Trouble, Usually Serious. It reckons that you should grease one set of joints once a month. Well, that's if you want to change them every 6 weeks. Through regular use of the car, I worked out that if I greased the universal joints in the drive chain once a week, then I didn't have to replace them on a weekly basis or 6 weekly basis. I could probably, the ones that are in there now are the same ones as I put in 10 years ago because I've maintained them all the time. So I do more than the manufacturer suggests because I understand how the thing goes wrong. How often do you replace parts? Those without a maintenance system, when it breaks. Those with a maintenance system, a lot of the time they replace them on inspection. Is this component looking like it's about to fail? We will replace it. So they're getting more use out of their components. One of the key findings was that you should involve the operator in maintenance. This chart shows how important different aspects are. We asked the respondents to identify what they thought was the most important. The most important thing was that maintenance had to be part of production. It wasn't something that was an add-on, it had to be integrated into production. One of the most important things. You needed to do standard things like have checklists to make sure everything was done. You had to have standard procedures that everybody did things the right way. Sounds just like total quality and quality maintenance we discussed at the start of term. You have to have a top-down priority. The senior management must support the maintenance. On one site we went to, if you wanted to take away a maintenance slot from the maintenance team, you had to have the signature of the managing director. It stopped the number of times that the production department, when they were running late, said, oh, we're not going to let you have the machine for maintenance. They had to get the signature of the managing director. An important thing was matching tasks to skills. It's not the most important or very high, but it's important to match the skills of the operators to the tasks that they were going to perform, or training them accordingly. It's interesting, it's one of the highest categories when you put almost as high as being part of production, when you put both being high and very high together. So it's one of the most important things. So, what did we find from this study? The top priorities for maintenance has to be an integrated activity. It has to be planned in as part of production. It has to have priority from the top. The senior management has got to support this. You have to have a good management system. You have to publish checklists. You have to have standard operating procedures. It's exactly like the quality and the management systems we've talked about already. And you had to involve the operator. You had to have operator-involved maintenance. You can have a maintenance team. They go round and they check everything once a week. if you train the operator on what maintenance should be, they can check every day. They can check every minute. So instead of having a small maintenance team, you suddenly have a huge maintenance team. You need then to give the people the staff training and give them the tools to do the job. You need to match the tasks that they're delivering to the skills that they have. They need to know that at certain jobs they have to call in a specialist. They have to be given top-down priority. The operators in one plant that we visited had the authority to stop the production line if they thought the equipment needed maintaining. So, for a successful maintenance program, it has to be an integrated activity driven by the need to improve. You have to have a management system and you have to involve the operators. So, I hope this section has given you insight into maintenance and maintenance procedures, age-related failures and how they relate to other topics.